Alright class, so this is the video for the extra buffer practice question that is posted on the chapter 16b slides. So I've printed out the question here. It says, what is the pH of a solution that is made by combining 25 milliliters of 1 molar acetic acid? So right here, acetic acid HC2H3O2, that's the formula, chemical formula for acetic acid. 25 milliliters of sodium acetate. So sodium acetate, the sodium is just going to be a spectator ion. So the acetate ion, C2H3O2 minus, that's really the piece that we're interested in. So I'm going to write that C2H3O2 minus out. And 5 milliliters of 3 molar HCl. So HCl, immediately I'm thinking strong acid, right? So that's going to be a source of H+. And then I've given you the Ka for acetic acid. So if I dissolve this acetic acid in water, right, this is going to be the Ka that governs that equilibrium. And I know that that's a weak acid, right? So the first thing that we need to do, first thing we need to think about is if I put these, chemical species together, what's going to happen? What chemical reactions are going to occur? And right away, I notice that HCl is a strong acid. So the reaction that I'm going to sort of deal with first will be H+, right? So HCl is my source of H+, plus my acetate ion is going to react to completion to give me my acetic acid back, right? So this is really, sort of what happens when we have a buffer. If we have a buffer and we add strong acid, that strong acid will react with the weak base. Likewise, if we add strong base, that strong base would react with the weak acid. So here, my strong acid, HCl, will react with the base to give me my weak acid back, the conjugate acid. And again, this is a reaction that's going to go to completion. And I know this simply because I've got a strong acid. I'm reacting a strong acid with my base, so that will drive the reaction to completion. So this reaction will go to completion. So this becomes a stoichiometry problem. This becomes a limiting reactant problem. So going back to Chem 121, my moles of H+, and always when I'm doing this stoichiometry table, so I'm going to just write start and end. So I'm going to start with a certain number of moles of H+. In this case, that's 0.015 moles. Certain amount of moles of acetate ion, 0.025 moles. And then the same amount, 0.025 moles of acetic acid. So at the end of this reaction, my H+ concentration, or my number of moles, is going to go to 0, right? And I know that, again, because this is a strong acid, this reaction is going to go to completion. I can see that this is a 1-to-1 molar ratio. So whichever one of these is smaller, that's going to tell me what my limiting reagent is. That's H+, so that will go to 0. At the end of this reaction, I'm going to end up with 0.010 moles of acetate ion, right? So if I take 0.025, I subtract that amount of H+, this will be my moles of acetate ion. And for acetic acid, now I'm going to add this in, right? I'm going to add in 0.025 moles plus 0.015 moles because I will be producing acetic acid. So this will end up being 0.040 moles of acetic acid. So now these number of moles of acetic acid and acetate ion, this is what I'm going to then use in my ice table to sort of finish this up and solve for the final pH. At this point, I could also use the Henderson-Hasselbalch equation, but we're going to talk more about that as we move forward. But this is a buffer, so the Henderson-Hasselbalch equation would also work in this case. But if I want to use my ice table, the first thing I'm going to do is convert back to molarity. Again, this is not always going to have to, you're not always going to have to do this in order to get to the right answer. But if you're not doing this, then basically you're skipping some steps, and if you're getting the right answer, you're sort of getting lucky. In most cases, it will work out just fine. But I think just as a good rule of thumb, it's a good idea to convert back to molarities. So for acetic acid, now we need to find my total volume, right? Because my molarity is going to be my number of moles divided by my total volume, 25 milliliters, and 5 milliliters. So my volume is going to be 0.055 liters. And so for acetic acid, this is going to equal 0.727 molar. And for acetate ion, I'm going to do the same exact process, and I'm going to end up with 0.182 molar. The last step then is using my Ka and to figure out what my final concentrations are. So HC2H3O2 plus water gives me H3O plus my acetate anion. And I've got the Ka for that, which was given earlier. It's 1.7 times 10 to the minus fifth. My initial concentrations, these are going to be my new initial concentrations, right? So in this problem, we dealt with a reaction first. So that's this first reaction up here. And then now we're dealing with the equilibrium, right? The equilibrium here. So 0.727 here. This is going to be approximately 0, and 0.182 here, minus x plus x plus x, just like we're used to doing. And then I can write out my Ka expression. Okay. So at this stage, right, I've written out my Ka expression, and my plus x and minus x, I'm going to treat those as negligible, right? Again, I think that that's a good thing to do simply because my Ka is very small. I expect this to be a very small x value. Once I solve for x, again, always I can go back and double check, make sure that that was a valid assumption. So my concentration of H3O plus, my x value, 6.8 times 10 to the minus fifth. Definitely this plus x and minus x terms can be treated as negligible. This equals my concentration of H plus, and then my pH is equal to 4.17, and that is my final answer. So at this stage, right, what I really want you guys to do is, if you've followed through this and you sort of, you know, can follow along and everything makes sense, that's great, but really you sort of, at this stage, once you do have the correct answer, a really good thing to do is go back, you know, read through the question, think about why you did what you did, you know, what's the significance of finding moles here, why is this a reaction, you know, why do I have this written as reaction that's going to go to completion, how did I do this, you know, what's going on with this entire table here, why did I convert back to molarities? That's a great question. The reason I converted back to molarities is because in my Ka expression, these values really do need to be molarities. Now, again, in this case, if you didn't do that, you would end up with the same answer. It works out, you know, because mathematically the ratio is going to be the same, but it's just a better idea to just always do this and in terms of molarities. All right, that's it for the extra buffer practice explanation.